Welcome everyone to this workshop. My name is David Power and I'm the HPC and AI specialist here at EscherCloud. And this evening I wanted to take you through a brief little run through of how we see AI's usage increasing across a broad suite of domains, and how it could be applicable in this hackathon environment as well. I'll also run through a little bit of a demo on using some of the technologies. So we have a Hpc cluster environment as well as a Kubernetes cluster spun up, and I'll run a brief demo on there also just to show you how to use and interact with the tools as well. So with that said, let me start by sharing off my screen. Okay, excellent. All right, so let me just quickly introduce EscherCloud and part of what we kind of stand for and what we're all about. So we're really on a mission to disrupt the cloud industry and data center landscape by really looking at how sustainability can be built into every aspect of how we co-design our environment. So first and foremost, we want to ensure that we're using things like renewable energies, and also that we have a mantra around working with circular economies and ensuring that we capture all of the heat that's generated from that and putting it back in as a green energy source in itself. We're building out a cloud environment which will allow for very sustainable AI for good to be run on top of it. And really our mantra is to be incredibly sustainable in terms of bringing this kind of service to market. So that's a little bit about ourselves, and I'll dive into the rest of it now. Okay, so I'm to start with, I just wanted to paint a bit of a landscape picture for where we've seen computing come from and where we think it's going to go in the future. If you look at the evolution of computing, I think back in the late 90s, you had this whole PC internet where there was potentially around 1 billion users that were connected up to the internet and formed the early stages of that. As we moved into the 2000s, mobile adoption started to significantly take off, and the likes of cloud services started to establish themselves. And as we look towards the future, we fully feel like between the combinations of AI, IoT, and edge computing, we're now going to enter an era where we're going to have billions, if not trillions, of devices connected to the internet, communicating with one another. And we're going to get to a stage where it's not going to be possible for humans to perform that amount of interaction. So a lot of this is going to be machine driven and AI driven, where machines will speak to one another to conduct whatever line of business they need to go about themselves. So we feel that that's kind of where the world is going towards, and that's been part of the core design principle of what we've been building at EscherCloud as well. AI, as a HPC practitioner, I've long said that AI is one of the killer applications for HPC, and it's pervasive across a very broad range of industries. I think one of the more interesting areas here when we look at kind of healthcare and fighting coronavirus, given the current landscape. If you look at what the team were doing at the Technical University of Munich in collaboration with the likes of Oak Ridge and NVIDIA, they were taking, they were mapping 3D proteins, mapping 3D protein shapes to determine their functionality using AI. And if you look at 1D proteins, there's been over 250 million discovered, but only 1.7 million of those have actually been 3D mapped. So it's a fraction of a percent. And that gap keeps growing as discovery is far more straightforward than the computationally demanding task of mapping it. So using AI, researchers are finally able to kind of close that gap, which is again one of the grand challenges of computational biology. 3D mapping, of course, enables the discovering therapies that can bond to proteins and neutralize its functionality, as the proteins in the virus that cause COVID-19 are human proteins the virus uses to replicate. So it gives great insight to researchers into how these viruses behave and how they interact, and helps us understand and then combat it more effectively. So thanks to supercomputing and AI, I think the reason we have a vaccine in the course of a year rather than 10 years has been down to supercomputing and AI. Of course, moving across into the consumer space, Facebook is one example of many, but I think if you go across between chatbots and recommendation engines and natural language processing, there really isn't a device that consumers are using that isn't being affected by this, whether it's Alexa that you're speaking to downstairs to turn on the radio, or using your social media contacts to interact with and chatbots. AI is pervasive across all of these verticals. And of course, IoT is one of the emerging areas as well. So when you look at kind of distributed and edge computing, the ability to take AI trained models, shrink them down, run them out at edge environments close to where either devices or data is being generated, again, opens up a huge new market for organizations. And the example here is around GE saving over 6 million a year in terms of reduced risk and outage, thanks to the application of AI out at the edge with IoT devices. Okay, so this brings me on to the rise of GPU computing. So going back over the years, of course, we kind of look at Moore's law and the performance of single-threaded cores and applications. The per-core performance and single-threaded performance has kind of tailed off over the last number of years, and we've seen this with the adoption of multi-core technologies. But the the gigahertz frequency really isn't increasing at all. When you look at GPU performance acceleration over the years, you can see this exponential. So this is a logarithmic scale actually on the left-hand side, but you can see this exponential growth in terms of performance that GPU has been providing as part of this. But yeah, one of the main drivers, of course, of the adoption of AI, when you combine the amount of data that is being generated, to actually make sense and process that, you need to have an equally capable amount of computational capability alongside it to process it. And given the exponential increase of GPU performance over the last number of years, we find that this is now one of the prime candidate architectures to go and employ and adopt and crunch these AI algorithms for consumers and users. If you look at AI supercomputing leadership, it's not just AI. If you look at the high performance computing space over the years, we take a look at traditional HPC applications such as NAMD and GROMACS for molecular simulations, Chroma for physics. GPU acceleration provides substantially higher performance thanks to advances both in terms of software and hardware. So you can kind of see from the graph there, there's the same architecture mentioned across different years, and a lot of optimizations have actually been applied in software. Models have been optimized, CUDA libraries, maths libraries have all been optimized as well to take more advantage of the hardware. So when you look at the combination of software and hardware optimizations, you're seeing like an 11x improvement for traditional HPC applications over the last 5 years or so. Moving across to MLPerf, I mean, this is one of the industry standard benchmarks that's used for machine learning. And again, the NVIDIA platform has claimed the top spot there for its training and inference leadership across a suite of tests there. Moving across onto data analytics as well. So looking at the Rapids stack, which kind of deals with more of the data analytical side and can help accelerate things like Dask and Spark Tree. These benchmarks were performed on a 10 terabyte data set, and again, you can see when you compare it to just CPU and even previous generation GPUs, we're starting to see some significant acceleration of results. The last one I wanted to mention here as well is the energy efficiency use case. So again, with sustainability being one of our core design principles here at EscherCloud, we wanted to ensure that we were selecting the appropriate architecture for the job, not just in terms of performance. And if you look at this, there's a top 500 list which measures the fastest supercomputers in the world, but there's also a sister list called the Green 500, which measures the amount of performance per watt that's delivered by these fastest supercomputers in the world. And again, GPUs deliver a significant amount of performance per watt. So when you're looking at performance per dollar per watt, there really is no better architecture for the line of work that we're kind of working in at the moment. Okay, so I mean, GPUs form one part of the overall data center platform. Really, you need to have quite a complex software stack on top of it to allow for a diverse range of applications to be run on top of it. And thankfully, we'll be there is quite a rich ecosystem of software libraries and frameworks that are available. And we'll be working through a couple of these later on. So you can see over on the operator side there, we have the Kubernetes logo. We'll be using CUDA as part of all of the GPU acceleration work that we're doing with our TensorFlow demo a bit later on. So you can see inside the AI training and inference, there's a number of applications that are in there. And of course, over on the software side, Ngc, I'll be touching on that a little later on as well, which is a software repository of certified containers and pre-trained models that allow for scientists to get up and running very, very quickly and focus on the research rather than the administrative effort involved in setting up these complex environments. Okay, so we're at the era of exascale AI supercomputing. And I guess what we mean by this is that AI is actually one of the new growth drivers for modern HPC. And we can see that reflected in some of the larger systems that are being rolled out, not just across Europe, but across the world. These systems are being designed to run very large training models and AI workloads at its very, very large scale. Part of the driver around the hardware optimizations in here, of course, been around this Tensor Core, which has been integrated into a number of these more recently released GPUs. And these allow for mixed precision workloads to be executed at a fairly significant rate. But when you look at double precision, we're going to hopefully hit the exascale mark in the next year or two. But already with AI performance, we're well over the exaflop with current architectures today and current systems. So I've mentioned these Tensor Cores. Historically, I guess supercomputing and HPC environments have had a fixation around just working with very, very high double precision numbers. But when you look at the ability to accelerate workloads by reducing the precision for computing, you can actually start to see quite some significant gains. And while the double precision is certainly necessary in some aspects, when it comes to image classification or natural language processing, you can get a suitably accurate response lowering the precision. And every time you lower the precision, you can increase the performance. So when you balance out the performance with the precision, having this dynamic mixed precision capability can actually help accelerate and improve the accuracy of lots of training models. So that's one of the hardware advancements that have been made on the modern GPU architecture, which we rolled out in our data center to support a wide range of scientific and AI workloads. Very good. So we can kind of break down AI simplistically into kind of two areas. And on the one side, we have the training portion of AI. And this is typically where you take a data set which has some labels set against it that can be used for kind of reinforced training of your neural network. So this is where you actually feed it in labels and data, and it can actually generate a neural network of itself to go and work out what needs to be inferred at a later time. Again, this is quite an expensive operation. And when you start to look at doing hundreds of millions of images, you can quickly run out of computational capability incredibly quickly. So this is one of the main tasks that we tend to run on big centralized supercomputing environments. And inference is where you actually take that trained neural network, run it possibly out at the edge or closer to where your users are, but they do the processing of information in real time and make a deduction based on that input from the trained model data that's brought into it. So again, we've got tools and applications that support both the training of models and of course running those then as a service for your inference workloads as well. So I dropped this slide in as it has a nice amount of coffee cups in there. And it kind of shows, a day in the life of a kind of an AI/data scientist. And if you're iterating through trying to optimize your model, on the one hand, it could be great to have lots of coffee breaks, but when you're working on CPU-powered environments, that time to result, it can be quite substantial when you're working on slightly larger models. The idea that being able to accelerate it to a point where almost it becomes an iterative process where you can do continuous improvement throughout the day, test and validate your model, relatively quickly and repeat it with alternative data sets and unseen data sets. I mean, the kind of results speak for themselves. The idea here is that engineers get to go home on time as planned once you're using the right hardware, architecture, and software stack to go and achieve that. Okay, so I mean, with that said, I mean, AI is kind of enabling broad enterprise transformation as well. So, I mean, we've spoken about HPC and kind of some of the scientific workloads, but I think you can look across pretty much all enterprise applications, and there's not just AI having an impact, but there's also a comprehensive framework and software stack that can help organizations and users develop solutions for these verticals. And like with conversational AI, there's the Jarvis framework. When it comes to autonomous vehicles, for example, there's the Drive framework, and all of these will be available on the EscherCloud system and the NVIDIA GPU cloud as well, for, again, enabling scientists and researchers to get up and running quickly with their environment and get down to focusing on the science. Okay, so listen, with that said, I wanted to switch gears slightly and speak a little bit more about the technologies that we're going to be using as part of this demo and workshop. So for this, we're going to be looking at what are containers, what's Docker doing, Kubernetes, and even Ngc itself. Okay. So it's probably out of the scope of this workshop to drill too deep into these topics, but I'm just going to briefly introduce them as a kind of a high-level concept. Containers have been around for quite some time. Their main purpose is actually to kind of standardize packaging for software and ensure that the appropriate libraries, link libraries, and dependencies are all packaged together with the application, so that it's easy to move your application from environment to environment. It also helps in terms of isolating applications from one another. So I think historically, if you looked at how legacy applications were built, you tended to have quite a bulky virtual machine or VM or even physical system. That would have had lots of different applications installed on the same environment, would have been quite complex to manage, and would have been not fairly difficult to port and migrate around from different environments. Part of the benefit of containerization is mobility, and that allows you to bring your application to where the data set is. I think we're at a little bit of an inflection point in computing, where rather than people bringing data sets to where the computational capability is, thanks to containerization and application mobility, improvements in networks and edge technologies, we're starting to see a shift in terms of people bringing their packaged applications now to where the appropriate data sets are. And yeah, Docker, so containers, and Docker is one of the main ones that we tend to use as part of this as well. So again, part of the benefits are to do with size. So if you look at a traditional virtual machine, you have, each VM has its own guest operating system. Within a container, we share that host operating system and kernel, and we just pass through or just have the application plus the libraries and binaries stored in the container. So that makes it much more lightweight, less overhead, much easier to copy and migrate and move around the place. And this is actually what the NVIDIA GPU cloud is actually based on. Okay, the last one we're going to look at now is Kubernetes. So once you've got this concept of an application and container, what is needed to be done now to actually go and orchestrate and run that application out in the respective cloud environment? So Kubernetes was something that had originated from Google, and it was really designed to run services at scale within their cloud environment. So it's a production grade container orchestration engine. And this is really, it's kind of the brains of the infrastructure, where you can just give it an instruction. For example, you might want to say, I want to run 3 instances of my AI inference service, and they can be located across different locations. And Kubernetes will actually handle all of the scaling and self-healing as part of that. So if something crashes or dies or something goes wrong with some of the hardware, Kubernetes will actually detect that as an issue and then respin up an additional container and load balance between those as part of a service-oriented mesh architecture. So we're going to be using this as part of the demonstration. Okay, and yeah, I've mentioned the Ngc Catalog. So this is essentially a registry of containers, pre-trained models, application frameworks, Helm charts and collections, which are all freely available to go and download as part of this hackathon. So we can go in and use Docker to go and pull, or Kubernetes to go and pull these containers, and even possibly pre-trained models if they're appropriate, and just go and start using them and running them within the research environment that we're providing. Okay, so with that said, let me just speak a tiny bit more about, so these, again, the benefit of these containers versus what you might find, say, out on the likes of Docker Hub or from building your own, is that they're enterprise ready, so they're optimized for the hardware that we're actually running on. They're scanned for malware and vulnerabilities, and of course they're backed by enterprise support as well. They've had a huge amount of engineering effort in terms of optimization and performance benefits, and essentially we can deploy these anywhere. So they're actually backed by I think a Docker registry, and I'm going to show you two use cases where we use Singularity in a HPC environment, and also look at Docker in a Kubernetes environment as well. Okay, so I'm going to quickly now show you guys the different environments we have. So I'm not going to, the VM is quite straightforward, so I'll just explain that in terms of how we use a Docker pull and Docker exec just to go and run containers on there. And I'll show a quick version of what we do on a HPC environment and a Kubernetes environment. Okay, so a couple of links to tools just in case you need to install anything prior to this. I know this has been recorded and people may watch this back, but if you want to get kubectl, the tools link there will give you all the information that you need. And of course, if you want to go and have a look at the container registry, that is also available at that link. Okay. So let me stop my share just for a minute and get my demo prepared. And the first demo we're going to go and look at is a demonstration on a HPC cluster. So let me share my screen again. Okay, and play that. Okay, in this demo, we're going to go through the use case of a HPC cluster. And this environment, we have a small Linux cluster set up, which has the Slurm workload manager pre-installed and configured, and it also has the Singularity container runtime environment set up as well. So we just use our SSH client to connect in to the head node, and this will be the server that you submit your workload and jobs from. Workload will then be executed on one of the compute nodes, which is handled by the Slurm environment. So one of the first things you'll notice when you log in is that if you try to run Singularity, it'll see that the command is not found. So we use a modules environment to store and package all of the applications that are available on the system. And you can see here we have Singularity available as one of our modules. So we do a module load Singularity, and then you'll see that the command is available to be used afterwards. Okay, so for the purpose of speed, we've gone ahead and downloaded the Tensorflow image. But let me just give you an example of how Singularity can actually work when pulling from a standard Docker, a Docker Hub container. So when you want to use Singularity, you can run it with the pull command, same as you would with Docker, and you just put in Docker as part of the address that you want to go and pull the image from. This will go to Docker Hub and pull the container for you. So this can be done against Ngc and any of the containers that are available in there, given that a lot of them are 5 or 6 gig. for the sake of the purpose of the demo, we'll stick to just using small ones. So you'll see at the start, we had, essentially a number of blobs were pulled down as part of it. These are the different overlays as part of the Docker container, and it combines them all into this SIF file, right? So this is the singularity image format. You'll see it's created a single file here. So this file is now your container application environment. And we can use standard singularity commands to go and execute that afterwards. So just as a quick example, I can do singularity run TensorFlow latest. Okay, and you'll see that this drops me into the TensorFlow container. So from within here, I can go and run my TensorFlow applications. So for example, if I just did, actually the other thing to point out as well is when you're running containers under the singularity environment, this HPC environment is set up to be a multi-tenant, multi-user environment. So it prevents you from running any containers as root, and that's part of the security implementation of a singularity. So it runs as a non-privileged user or standard user when you're within the system. So when I'm in here, I run my ID, and you can see I'm still that or support user. Okay, so if I wanted to run in, just show you a quick version of TensorFlow, so I can run my Python in here, import TensorFlow as TF. Okay, and then we can do just say print TensorFlow.version. Okay, so we can see here that TensorFlow is working. You can see that we've got version 2.5, and the container is working as expected. Okay, so let's see, start release. The other thing to note as well is this container is a Ubuntu 18.04 environment. And when I exit back out to my head node, you'll see that this is a CentOS operating system. So you can see we're running a Ubuntu container on top of a CentOS environment. Okay, now the next thing we're going to do is we're going to show you how to submit a job to the workload manager. So if I run the command sinfo, you can see within our environment there's a small 2-node environment that's set up here, and there's a partition called the default queue, which is used to run standard applications. I can run the command sq as well, and this gives me a quick look at what jobs are already active on the system. And this pretty much just confirms that the system is idle at the moment. Okay, so within here you'll see I have a couple of submission files. So we're going to submit a TensorFlow job to Slurm. So let's just have a quick look at the parameters in here. So at the top of the file you can see we have a couple of directives that are defined, which Slurm will interpret as resource requests for the particular job application. So we're essentially giving it a name, defining the output file that we want, telling the job to run on the default queue, and I'm essentially saying that I want a single node, a single MPI task. So these will change depending on however many cores and nodes you require, and of course give it an expected runtime. This is optional. In my submission script, this is just a list of bash commands that we're going to go and run on the node that executes. So to start with, I'm just going to check all of the environment variables that are set by Slurm. So this will tell me a couple of interesting parameters around the job, what node it was run on, and so on. I'm going to clear out my modules environment just to ensure that nothing gets inherited from the environment when the job is running, and load up Singularity, do a quick module list, and then we're going to essentially run our Singularity file. We're going to call the Python interpreter once we load up the container, and we're going to pass it a Python script to go and execute the TensorFlow commands. Okay, now because this is a fairly quick job, we're going to set it to sleep for half a minute while we just go and check some of the Slurm commands that will confirm that the job is executing and running on the system. Okay, so let's get back out of that. Again, just to show you quickly, our Python script is exactly what I ran previously. We just import TensorFlow as TF and print the TensorFlow version. So again, this is just an easy, representative, quick job to show and illustrate how to use Slurm in the system. Okay, so to submit our job, we run sbatch submit TensorFlow job. Okay, and you can see we have a job ID of 39. So immediately you can see that I've got an output file has started to be generated. If I look at SQ, you can see that we have a job that's been running for the last 10 seconds and it's been allocated on node 1. sinfo minus nl just confirms now that node 1 has been allocated. And if I did a tail minus f tensorflow.39, you can see that this is essentially showing us where we are in terms of the job. So it's just caught it in time of the sleep. Sleep has jobs completed, going to sleep, and the job completed as well. So we can control C out of that. When I check SQ again, you'll see there's no jobs currently active on the system. sinfo minus nl. You can see our two nodes have returned back to an idle state. And we can check our output file to confirm that the job ran as expected. Okay, so you can remember we did this set and grep for slurm as part of the environment variables. So, this lets us know some of the parameters around the job execution. So it just confirms, for example, that we ran on node 1. We then went in to list the modules that were loaded. We've no modules loaded. And then we loaded our singularity module. We ran the TensorFlow script that told us what version of TensorFlow we were working at. Job completed, confirms the time and date, and exits normally. Okay, so that's a very quick introduction to using Singularity and Slurm in a HPC environment.
Excellent. Okay, so that was the first of the demos. Yeah, as I didn't trust the live demo gods, I pre-recorded them a little earlier today. So let me just move on now to the next one. And in this next one, I'm going to speak about the Kubernetes use case environment and how to interact with that as well. So let me share this again. Desktop 2. Very good. And in this demo, we're going to take a look at our Kubernetes cluster environment and interact with it via the kubectl CLI tool. And we're going to use NVIDIA's GPU cloud containers to go and run on our Kubernetes environment as well. Okay, so to start with, I've installed a couple of utilities locally here on my system. This is a Mac. You can use Windows or Linux as well. You can go to the respective kubectl installation guides for guidance on installing those. But for Mac, we just needed to do a brew install Helm, which is already updated. Okay, so that's already installed. Likewise, kubectl. Whoops, spelled that wrong. Cool, we can see that that's already installed and up to date as well. So they're the two utilities that we're going to use during this workshop. And let's start off by actually just having a quick look at our configuration file. So when you're given access to a Kubernetes environment, you'll be given a configuration file which includes certificates, usernames, and access passkeys to allow you to access the environment. We've got our Escher file here, which includes that information. So if I just do a quick head on that and grep user. Okay, you can see, we're accessing the system here as the kubadmin on the system. So the other thing I'm going to set is a quick environment variable so that I don't have to pass that configuration file to kubectl every time I want to go and run a command. So we can just do an export kubeconfig equal to Escher. Okay, and with that then I can then run basic commands, kubectl get nodes. You can see here I have a small little cluster. It's got a master and a standard compute node that I just spun up a minute or two ago. And we can do a kubectl get pods. Okay, so actually I've already got a TensorFlow job running. Let me just delete that. Delete pod tf. Okay. So one of the first things we're going to do now is we're going to launch a quick job here. So I'm going to just show you one of the files that we'll be using. I'm in the same directory here, and we're going to have a look at small test. Okay. So this is an input file that is passed to the Kubernetes orchestration manager, and this instructs Kubernetes to go and run a TensorFlow container. So actually, let me also bring up just very quickly to show you guys the NVIDIA ngc.nvidia.com. So when you go to this URL, you will be presented with essentially a library of containers and collections and Helm charts that are freely available to download. So we're going to use the Kubernetes, the NVIDIA provided TensorFlow, because it's optimized for GPU and CUDA environments and comes with all of the appropriate libraries and acceleration built into it. So if you go to NGC, I know I've just searched for it there, but you can actually filter and type in the container that you're looking for, and then click on the actual environment itself as well. So when you click on the application that you want to go and use, you'll see there's a pull command, and that gives you essentially a URL that we've injected into our Kubernetes input file. So you'll see that this here, the image name corresponds to the nvcor.io location that we got from the NVIDIA GPU container library. This catalog is also quite useful because it gives a little bit of information about the utilities that we'll be using, and a couple of parameters on how to actually go and execute and run these containers in your local environment as well. So for example, if you were just running it on a single instance and just using NVIDIA Docker or Docker, you could follow these commands to go and run and execute the job as you see fit. But that's a very short intro to NGC. Let's push that out of the way here. And you can see then further down here we have some resources. So you can see I'm actually requesting GPUs as part of this Kubernetes environment also. Okay, so with that said, what we can do here is our environment is deleted, kubectl get nodes. Okay, and then kubectl, so we want to create and pass it our file, small GPU test pod, and we're just going to do the NGC one for this stage. Okay. So you can see that has now created a pod, and a pod is kind of a unit of work that's defined within a Kubernetes environment. So I can do kubectl get pods. You can see that that is now in an up and running state. I can also do a describe on it, which will actually show me what's been happening under the hood as well. So you can see here, it gives a bit of information on the top around what it's running, its name. You can see it's confirmed that it's pulling from the NVIDIA GPU Cloud Catalog. It's in a running state, and the command that we're actually getting it to execute is just a sleep command so that we can get in to the container and perform some operations in there at a later date, which is just being, we're just doing that for the purpose of the workshop. And you can see the resources that have been requested as well. We're looking for that GPU. You see here down the bottom, this is essentially the events log, and you can see that we got assigned to one of our nodes within our Kubernetes cluster, so demo node 1. And again, this corresponds here to this guy here, which is part of our cluster. So we have a master which orchestrates the environment, and the nodes which are our minions which do the actual execution of the workloads on top of it. Okay, now this went through relatively quickly. We had our container pre-loaded for the purpose of speed of this demo, and we also had the node pre-provisioned as well. What you may see within the workshop environment is when you do a get nodes, you may come across an instance where there's just the master node reported. That's because we have cluster auto-scaling enabled within the platform. So additional GPU nodes are spun up whenever they're requested, and Kubernetes auto-scales based on the number of resources that are requested or the number of jobs or pods that have been requested by different users as well. So it's an auto-scaling technology to ensure that we're only using the resources as and when we need them, and that they're automatically deployed in response to workload requests. Now, when you log in for the first time, that node may not be provisioned, and I'll just give you a quick look at the events log of what happens with pod auto scaling. Okay, So again, I was just running the kube control describe pod, and I go down to the bottom here. So you may see if the nodes are not pre-provisioned, what you'll see is the scheduling will fail. So you can see here it was looking for a certain node. It says there's 0 nodes available. You can then see that the triggered scale up happened after about a minute, and essentially we requested a GPU, and that provisioned the node for us. And then in the course of maybe about 4 or 5 minutes, it spun up an additional node, provisioned it with all of the Kubernetes environment that was required, pulled down the GPU TensorFlow container, and started the actual container workflow. So you'll see auto scaling enabled within the platform, and it just takes an extra couple of minutes for that to go and execute whenever it's being used. Okay, so now that we have, let's have a quick look here, get pods. So we can see TensorFlow is all up and running. So the next thing we want to do is, how do we go in and access this environment now that it's up and running? So again, we can use the kube control for pretty much most container-based manipulation. And what we're going to do here is just log into the system and have a quick poke around with it. Okay. So for that, let's say, for example, we just wanted to execute a command on the environment. We can use the kube control exec IT for interactive, pass it the name of the container you want to run in, and then maybe let's just run something like NVIDIA SMI to have a quick look at the GPUs that have been detected in there. Okay, so you can see we have our CUDA driver installed, Quadro card detected, no processes running. So we've essentially passed this NVIDIA SMI command into the container to execute for us. Now we can also do that by just passing bash here. So if you wanted to just essentially drop yourself into the container. We're now in the Kubernetes demo node 1 server on the TensorFlow container, and we can actually run that same command from in here now as well. Okay, so we can see the same output of that. Okay, the other thing as well to have a quick look at while we're in here, this has the TensorFlow environment fully set up and created. So if I wanted to go in and do anything sort of interactively, I can import TensorFlow as TF, and let's just kind of print the version quickly to just make sure it's working. Okay, very good. So we're running essentially Python 3, TensorFlow version 2.4. Okay, and then just exit out and we're back up to our local host system again here. Okay, now if we had some more sophisticated use cases, what would typically happen is you'd have most of your TensorFlow instructions in a Python script. So we've got a couple of those. Let me just jump over to this screen here, Python scripts. Okay, so I've got a couple of quick example scripts here. So Python print version is exactly what we just did, inputting it directly into the TensorFlow CLI. And we also have a small TensorFlow GPU matrix multiplication example, which confirms that we're using a GPU, generates 2 matrices, and does a reduction mean multiply across them as well. Okay, so if we wanted to copy those scripts up to our environment, again, we can use our kube control command, cp. Now we don't need a -or like you would do with scp for a recursive copy. It's automatically inferred when you pass it a directory. So let's do Python scripts, and let's copy it up to TensorFlow, and you'll notice that the area that we landed in a little bit earlier was /workspace. So let's copy our data up to there. Okay, and I'm going to just jump into the environment again and have a look. So now you can see we have our Python scripts folder up here. There's also a couple of NVIDIA examples and Docker examples that are provided as standard from the Ngc container, but feel free to have a little root around in those yourselves. When I go into the Python scripts, you can see all the 2 files that were here are here and available, and I can just run those now using Python tf print version. Okay, so that gives us the same output we had a little bit earlier, and we can do our our matrix multiply as well. Okay, excellent, and that's given us our results down here. And the other nice thing to just note as well is this, it does a detect on the device, and you can see it picks up the Quadro GPU as well. So you can see it running on the actual GPU itself. Okay. So that was a very quick demo on just how to spin up a quick container, run a quick job on it. Now, one of the other things to be aware of as well is that most containers, well, containers are ephemeral. So as soon as they're destroyed, all of the data is destroyed that's created in them as well. So that folder that I copied up, as soon as you destroyed a pod, if you recreated it again, all of that is deleted and it's non-persistent. So we have a couple of options that we can use with Kubernetes. We can either attach some local block device storage to the container for persistence, and this will allow you to reattach that same device to different containers in the future, meaning you don't have to keep on continually copying up your data anytime you create something new. And there's also an Nfs server that can be created within the environment as well. So I'll step through both of those scenarios now and take a quick look at how to create some persistent volumes within Kubernetes. Okay. So to start with, let me just jump over here to my folder again, and you'll see here I have a persistent volume claim. Okay, so let's just have a quick look at this. Again, it's a simple YAML file, and we're just going to speak to our storage backend and say we're looking for a 10 gig partition. So, very, very straightforward. So let's apply that. Control create. Okay, so that's created. Control, so PVC then to have a look at the persistent volume claims. Get PVC. Okay, very good. So you can see our cloudalized storage is up and running. Now, with that up and running now, what we can do is we can modify our pod creation YAML file and ask it to include that persistent volume request as part of the container creation. So again, if we have a look at our files here, you'll see that we had essentially our small pod with storage is our next one. So if I just did a quick diff on this, you can see here the only differences between those two files are that I'm adding a volume mount path, and we're just letting it know what the backend persistent volume claim name is as well. So we're essentially telling it to mount /data in the container and giving it that 10 gig block device that was created in our environment as well. Okay, so let me go back now and just delete our pod. We're going to get pod. Okay, delete tf. Delete pod. Okay, so that takes a couple of seconds to clear out, and once that's ready, we'll go and create our new pod. Okay, very good. So let's just check and make sure everything is done. No resources found. Excellent. So next thing we're going to do now is control create. SF small with storage. Okay, so the pod is created. Again, I'll just show you that full file. So that you can have a quick look at it. So again, very, very similar to our first file that we created, passing it a mount path, telling it what the persistent volume claim is, and hopefully now at this stage our pod should be up and running. That's good. Describe. Okay, excellent. Started, created, cached. Very good. Okay, so we can now go in and exec here. And if I have a quick look at df, you'll see now that we have a data partition mounted on dev VDB, which is the second virtual block device within the environment. So I'll have a quick look in /data. You know, it's a clean environment, there's nothing in there. So let's copy up our files again. kubectl, cp, Python scripts, tf, and we just pass it /data instead of /workspace like we had previously. Excellent. Let's jump back up into our container again and just confirm that everything is in place. Data, very good. There's our Python scripts. Python tf version. Python. Print version. Okay, very good. All as expected. Okay, excellent. So let me just delete that pod again and we'll move on to a quick demonstration of using an Nfs Share. Now, an Nfs Share should be used when you're running multiple containers. So this persistent volume claim is really only useful for a single container. It's a one-to-one mapping. A block device to a container is a one-to-one mapping. An Nfs Share is something that can be distributed and shared across multiple containers. So you can have a shared pool of a shared data set across multiple containers via the Nfs Share, and becomes more important as you look at kind of scale out workloads and distributed training. So let's delete our pod, delete tf. Oh. Okay, so while that's deleting, let me give you a quick view of what's happening with the NFS one as well. Okay, so again, we're passing, when you compare it to our very initial container pod, there's a small few modifications that are made to the YAML file. You can see here we've made a claim name of a NFS PVC, which we'll go and create now in a second, and telling it to mount that under /data. Okay, so this is where Helm starts to come in for this side. So we're going to use Helm, which is essentially a package management system for Kubernetes, and we're going to get it to install an Nfs Server within our environment. Okay, so a couple of things that we needed to do, and I've already done them in my environment. So I wanted to, we have the Helm utility installed from Brew a little earlier on, and I'm going to add a repo, so that already exists. So just putting that command up there so that you have it, and then we do a Helm repo update. Okay, so it shouldn't take too long as it was all done and dusted a little earlier. Okay, so Helm is now added to our environment, and what we're going to do is instruct Helm to go and create an Nfs server. Okay, so we're essentially telling it to go and install this from the stable repo Nfs Server provisioner, and we're passing it a few little parameters as well around our environment. So we're telling it where the persistent storage class is, giving it a size, and instructing another couple of variables as well. Okay, that might have been an error in my cut and paste. Indeed it was, so let me just paste that in properly again. So persistence true. Now, okay, so this should go off and install our Nfs server, so that's good. It's gone into the default namespace, it's deployed, so the Nfs provisioner service has now been installed. Excellent. Okay, so with that installed, in fact, we can probably now set up our Nfs pod. Okay, so let's kubectl create. And actually we can have a quick look, get PVC. So you can actually see here now we have, that was pre-provisioned from earlier anyway, but they're the steps required to go and set up your Nfs server. So let's create our container again. small pod with storage, NFS Ngc. Okay. Okay, so that's in a pending state. Oh, sorry, I need to create the persistent volume claim next. So one step backwards. Now that I've created the NFS server, I now need to create the actual Nfs Share itself as well. So the package and service has been added, but not the Nfs Share itself. So this is the YAML file that I'm going to apply to actually go and create that persistent claim. And you can see I'm just going to create a small 2 gig partition for our NFS PVC. So let me just jump back a little bit and create that. Okay, very good. So let's have a quick look here. Describe pods and guess. Okay, lovely. Our NFS PVC is here. Storage class NFS. Perfect. Okay, that looks a little bit better. Now, at this stage, you can see in the event log that when we initially scheduled the TensorFlow container, that it failed because the persistent volume claim could not be found. Now, Kubernetes was intelligent enough to realize this, and it continued to reschedule until that resource became available. So after we created the persistent volume claim, you can see that the TensorFlow container got created and started shortly afterwards. Now when I do a kubectl get pods, we should see that up and running. Okay, that's great. Now let's get into our TensorFlow environment again and take a look at it. So we have a df here, and you can see, we have a /data again, but this time rather than it being dev vdb, we can see that it's actually an NFS mount point. So this is the other Nfs server that's running in our Kubernetes environment, and it's done via the NFS mount. So if I grep, for example, NFS and etcm tab, you'll see that data is mounted via the NFS protocol. Okay, so that's a quick demo on how to use Kubernetes, pull containers from Ngc, and then attach either block or NFS storage to your environment depending on what your requirements are. Okay, so thank you.
Lovely. And that, you'll be delighted to hear, brings our little demo and workshop to a close. So I guess with that said,
feel free to ask questions in Discord and in the chat.
Excellent. Happy hacking. Thanks, everyone.
Cheers.
Bye.